single, double, triple bonds. Then we are going to get into how we can draw out two-dimensional shapes of covalent compounds or molecular compounds. All right, so first let's kind of look at a single bond. Now, with a single bond, we said how many electrons are being shared? 2. All right, so let's look at 2 chlorine atoms. Chlorine atom has how many valence electrons to it? 7. Okay. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7.
Can we use dots?
Yeah. Remember, with the electron dot diagram, you can use whatever symbol you want to. I'm just using X's and the dots so you can see the 2 different atoms. Okay? We look at our chlorine atoms. How many unpaired electrons does the chlorine atom have? 1. Okay? And how many more electrons does the chlorine atom need to get to reach the octet rule? 1 more. So since both of them have an unpaired electron, and they just need 1 more to reach the 8, what they're going to do is, with those unpaired electrons, is they are going to share them between the 2. And that's how we get a single bond going on. Now, if we look at how double bonds made, let's look at 2 sulfur atoms. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so how many unpaired electrons does the sulfur atom have? 2. Okay, and we need to reach 2 more, right? So let's first make a single bond. We're going to share 1 set of unpaired electrons between the 2. So now, how many electrons does each sulfur atom now have? 7. 1, 2, 3, 4, 5, 6, 7 for the one on the left. And if we count on the right, we should still also have 7 as well. If we take these last 2 unpaired electrons and share them between the 2, making that double bond, and if we count them up now, that both of them have 8 electrons. Okay? Questions? Any kind of questions there? Triple bond. Let's look at nitrogen. Nitrogen has how many valence electrons? 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So how many unpaired electrons does nitrogen have in this situation? 3. Okay? So let's go ahead and let's make a single bond between the 2 nitrogen atoms. How many electrons does each nitrogen atom now have? 6. Does everybody see that? Okay. Let's take another set of unpaired and let's make a double bond between the nitrogens. Now how many electrons do they have? 7. Then take our last set.
It'll have to be a straight line.
Does it have to be in a straight line? That's how they're usually represented.
So you have to like move
Yeah. So that we can see that, okay, they're shared between the 2. All right. So make a triple bond between the two nitrogen atoms. Now each of them has 8. Okay? Now I have a question for you. Single, double, triple, what would be the next step if we were to keep on going in this process? Quadruple bond, okay? Well, a quadruple bond, how many electrons will we have shared between the two atoms?
4.
Well, we make 4 lines, but how many grand total we would have? How do you think we should represent the quadruple bond? Well, single bond, I showed it with chlorine, which is in group 7, right? Double bond, I showed it with sulfur, which is in group 6. Nitrogen is from group 5. To show a quadruple bond, group 4. Okay, so we look at carbon, because carbon's in group 4, right? And carbon has how many valence electrons to it? 4. 1, 2, 3, 4. 1, 2, 3, 4. And how many unpaired electrons does each carbon atom have? 4. So if we kind of think about it, okay, well, all we have to do is just bond up the 4 from each side, right, to make that quadruple bond between them. Like that, right? Okay. Well, let me show you something. Sometimes we have to use models to represent what we're trying to write down on paper. Okay? So let's just say that these two white doohickeys represent chlorine. Right? So to represent the single bond, I just have this bar between the two. Okay? Now for a double bond, with these model kits, we have the bendy pieces. Okay? So to represent a double bond, I gotta use 2 of the bendy pieces. So here we have a double bond. Now if I want to make a triple bond, like what we did with nitrogen, how many bendy pieces do you think we're going to have to use with the triple bond? 3. Okay. Bendy pieces. Okay, now for a quadruple bond, I would have to use 4, right? Okay, here's a challenge for you. Pass this challenge, you get an A for the rest of the semester. And would you like to make some money? Oh, thank you very much, 8th period. They broke a piece. Okay, so anybody want to try the challenge? A for the semester. Okay, cool. All you have to do, get this into part of the bendy piece. There.
Can I have another bowl?
Nope. Because 2 carbon atoms, 2 carbon atoms. All right, I have a triple bond set up for you. All you have to do is just get this over there. You ready? Okay, now, kind of the story behind this. Just because we can write it down on paper, is it really going to happen in real life? Okay. There's a kid, when I was at college, he was 2 years behind me. His name, I think his name was like Matthew or something like that. And he was taking organic chemistry. He had the same organic professor that I had. Dr. Beffer, who's been over here from Iran since 1954. The man has 7, 8, 9 different patents on different organic compounds, which means that he made them. The last thing that he was doing before he retired was he was trying to make an organic compound, nicknamed Jaws, that would attach to cancer cells and eat them. Wouldn't that be nice? Okay, well, Matthew was in organic chemistry class, and he had about a 15-minute argument with a man that doesn't go by the book. He goes by what he remembers, and he knows a lot. Said that, well, since he can write a quadruple bond down on a piece of paper, that it must happen in nature. Dr. Bethruth said, no, he's wrong. And Matthew said, no, he was right, because he could write it down on paper. You can write down a lot of things on paper. You kind of think of all these cartoons that you've watched over the years and everything. You know, ever watch some of the classic ones? Cartoon character runs off the cliff and keeps on running even though there's nothing underneath of him. And then when he stops and realizes that there's nothing, what happens to him? He falls. But before that happens, he's still running on air. Okay? How's it going, Cole?
Oh, that's not gonna work.
Okay.
Just don't connect.
Alright, so what we're going to do next, like I said, we're going to learn how to draw molecules two-dimensionally. And this is called, I'm going to put this marker out here. Those structures. We're going to get through a lot of it today, but what we will do is on Thursday kind of finish up those structures. Then I'll show you how to go from two-dimensional drawings to three-dimensional drawings with these things. Okay? So let's kind of start off with really simple compounds to draw. Alright, so our first one is going to be CH4. First thing that we're going to do is we're going to figure out how many valence electrons we're working with total in our compound. And the way that we do that is break it up into the individual elements. So if we look at our chemical formula, how many carbons do you see in there? 1. Alright, so we're going to take the number of that element and we're going to multiply by how many valence electrons that it has. So carbon has how many valence electrons to it? 4. 1 times 4 is 4. Okay, hydrogens. How many hydrogens do we have in our formula? 4. And how many valence electrons does a hydrogen atom have? 1. So 4 times 1 is 4. Once we have done this for every element in the compound, we're going to add up our numbers. 4 plus 4 is 8. Okay, now with this I'm going to show you 2 different ways that we can do this. Okay? First way is the way I was kind of taught in college. It's a little bit cleaner than the other routes. And as we progress and we get into a little bit bigger molecules, you'll see why. Okay? So after we figure out how many valence electrons we're working with total in the compound, the next step in the process is we are going to draw what is called a skeleton structure. Skeleton structure, we have one central atom, and then we draw single bonds to all the other atoms, and they are considered to be outer atoms. Now, how do we figure out what is going to be our central atom? Majority of the time is we go with the element that we only have one of. Okay, so in this situation, our central atom is going to be carbon. From carbon, we're going to draw a single bond to each of the hydrogen atoms. after we have drawn the skeleton structure, the next thing is we need to figure out how many electrons we have used up so far from our cache. Okay, so we have 4 single bonds. How many electrons are shared in a single bond? 2. So 2 times 4 is 8. So we used up all the electrons that we possibly could have for this compound. Once we get down to 0, we have to ask, is everybody happy in this situation? Okay, now what do I mean by happy? For the elements that need to, have they reached the octet rule? Okay, so let's kind of start with our central atom, carbon. Carbon has 4 single bonds coming off of it, so it has 8 electrons being shared, right? So would you consider carbon to be happy since it's reached 8 electrons? Yes. Okay. Now, the hydrogens. How many electrons do the hydrogen atoms have going to them?
2.
2. Okay. Well, is hydrogen happy in this situation? And the answer is going to be actually yes. Okay. So there's a couple of things that we're going to put stars by so that you have those in your notes so you can say, okay, refer back to this. Hydrogens only have single bonds to them. Okay, and the reason why hydrogen are going to be happy with only 2 electrons, because once they reach 2 electrons, they start acting like what other element? What other element has only 2 electrons to it? Helium. Helium is a noble gas. And we said that noble gases are, starts with an I and ends with inert. Inert. Okay, they're happy, they're stable. Now another thing that we're going to put with hydrogen, hydrogen will never be a central atom. Okay, any questions right now? No questions? Okay, so now, the other way that we can kind of do this, and like I said, this is how I was taught in college. This is a little bit cleaner than doing this route that I'm going to show you. The other way that we can do this is starting off with the electron dot diagrams for all the elements. Okay? So we know that carbon has 4 valence electrons, so it would have 4 dots to it, right? 1, 2, 3, 4. Each hydrogen only has 1 dot. Then if we kind of set up this way, then we can kind of see, okay, so the valence electrons from this hydrogen atom is going to bond to this valence electron from the carbon. So we can kind of see that still, we're still getting 4 single bonds coming off carbon, or a single bond going to each of the 4 hydrogen atoms. Okay? Questions? Any kind of questions? Nope? All right, let's go on to our next compound. H2O.
We don't have to do the dot diagram way, do we?
No, like the way I'm going to do it is this route. Okay? I want to show you. We can also do it this way as well. Okay? All right, so for H2O, go ahead, try to figure out how many electrons we're going to be working with total for this compound. something you might want to do is maybe get your periodic table out, so you can have that right in front of you.
You have an extra
Hmm?
one.
Hydrogen
Mine has.
Yeah.
1 E minus.
I do.
So why on earth did we subtract 8E?
Hmm?
Why did we subtract 8E right here?
That's like after you're done when you put them in, you subtract it because there's 8 electrons out of there.
So we have to do it on this one too then?
Hmm.
Okay, subtract 8 all here too again. Or we have to do as many electrons.
Yeah, there's 8 electrons. 7. Did you actually draw the diagram or did you just do it?
No, I just.
Okay, yeah.
Yeah, but I don't know if we can minus 8.
It's like when you put it in, you just subtract 8, so you have 0 left over.
Did we come up with 8 electrons total for our cache? Does anybody have any questions on how I came up with that?
It's not about how you got that, but do you have to use all of the electrons in the cache?
Yes. Yeah. When we do all this, we should get down to 0 electrons remaining, no matter what. Okay? Now, another thing to kind of think about. Your number should always be an even number. If it comes up odd, recheck your math. Okay? Total number of electrons in the cache should always be an even number. If it comes up odd, check your math. Okay, so now, what's our skeleton structure going to be like? What's going to be our central atom for this situation? Oxygen. And off of oxygen, we're going to have a single bond going to each of the hydrogen atoms. Question, Stephanie?
I'm just confused.
About what?
I don't know. I got 4.
4, 4.
Well, you got 8.
Alright, so 2 hydrogens, right? 1 valence electron for the hydrogens. So 2 times 1 is 2. Oxygen, we only have 1 oxygen, right? It has 6 valence electrons. 1 times
How do you
6,
know that?
it's in group 6.
Got it.
Got it now?
Yeah.
Okay, alright.
Thank you.
Alright, so looking at our skeleton structure, how many electrons have we used up so far from our cache? 4, because we have 2 single bonds, right? In a single bond we have
2.
2 electrons. So 2 times 2 is 4. So we have 4 electrons remaining. Well, hydrogens only have single bonds going to them because they're happy with just 2 electrons, right? So the 2 hydrogen atoms are happy. How many electrons does the oxygen have? 4, because of the 2 single bonds. Okay? So guess what we're going to do with these 4 remaining electrons? We're going to put them on oxygen. Now, when we put them on oxygen, we're going to put them as pairs. Because electrons like going around in pairs. Now, these pairs actually do have a name to them. They are called lone pairs. Okay, so with those 4 remaining, put 2 lone pairs on oxygen. We're down to 0 electrons remaining. Is everybody happy?
Yeah.
Yes. Else?
Where did those 4 come from?
You mean right here?
Yeah.
We had 4 remaining. After we made our skeleton structure, we had 4 electrons remaining.
Okay.
All right, and then we put them on the oxygen to create with as lone pairs, so that oxygen could complete the octet.
Okay.
All right. Timothy?
Now, why are
He
they?
was trying to get to 0.
What electrons like to do in this situation? They like to go around
You
pairs.
don't have to draw that graph.
Okay. If we went back to the electron configuration, in every orbital, we'd always see the electrons in pairs. Okay. Any other questions right now?
No.
Nope. All right. All right, so for this one, figure out how many electrons we're working with total. Try to set up your skeleton structure. Not old. Okay. Just with these last 3. But the number of electrons, like I said, should be in these numbers, no matter what. All right.
And each hydrogen you have.
Oh, that's right. I mixed up.
8. Minus what?
No, no.
What do you 8?
It's always going to be an even number.
3 hydrogen.
It's just with these 2 examples, I knew they were going to come out with 8.
Can I see what you did?
These are some nice, easy ones to start off with, so you can kind of start seeing how this is going to be
I
working
don't know
out.
if I got it right. I think I did.
All right, so did we come up with a grand total of 8 electrons for our cache?
Yep.
Then for the skeleton structure, you put nitrogen as your central atom, and a single bond to each of the hydrogen atoms.
Yeah.
Okay? So how many electrons have we used up so far from our cache?
6.
6. So we have 2 remaining, right? Where should we put these 2 remaining electrons at?
Top of one is a lone pair.
On the nitrogen, because hydrogen's happy with 2, and before we put that lone pair up there, the nitrogen only had 6 electrons to it.
Do the lone pairs have to be on top?
It doesn't, I just put them on top because there's nothing up there. It's just, we just need to show that that lone pair is on nitrogen somewhere. You could have put it down over here,
Like the hydrogens too, it doesn't matter which one, like where you put it at, as long as
Right.
3 come off the nitrogen.
Right. This is, I could have put it like that instead, I'm just gonna put the lone
Okay.
pair right there because that's an open spot for me to draw on.
Okay.
Okay? Caroline, was that kind of your question as well? All right. So we used up the remaining 2 electrons. We're down to 0. Everybody happy? Yeah. Any other questions right now? Yes.
We might get to this, but I've been wondering since we did the last one, what if it was H2O2?
Okay. We will get to that.
Okay.
Probably not today. On Thursday. Okay? But yes, we will look at something like that. All right, next one, let's do PBR3. So what I'd like for you to do for this one, just like with NH3, figure out the total number of electrons we're working with, draw your skeleton structure, please stop. This is what we're coming up for total number of electrons.
Yeah.
Questions there? Okay, what's going to be our central atom? Should be phosphorus, because we only have one phosphorus. Okay. And drew a single bond from phosphorus to each of the bromines, right? Okay. So how many electrons have we used up so far from our cache? 6. So that means we have 20 electrons remaining, right? Okay, now, the difference from this one compared to our first 3 examples is that our outer atoms are not hydrogens, okay? So when the outer atom is not hydrogen, with any remaining electrons, what we're going to do is we got to complete their octets first. Okay? So each bromine atom has how many electrons going to it right now? 2. Right? Because it has a single bond. How many more electrons does it need to reach octet? 6. So we're going to put 3 lone pairs around each of the bromine atoms. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. The reason why we have to do that is we have to worry about the outer atoms and completing their octets first before we complete the central atom's octet. Okay? So we used up 18 from the remaining 20. We have 2 remaining. What we're going to put those 2 remaining?
A lone pair on P.
Yeah. So after we've completed the octet for our outer atoms, any electrons remaining will go as lone pairs on the central atom. Down to 0. Everybody happy? Yes. Ellis?
Why can't outside atoms bond to each other also?
It just doesn't happen. One of the reasonings for that is because of the electrons, the lone pair of electrons around them. Now, we already have them as pairs, but if we try to get this bromine next to this bromine with the electrons around it, it's going to cause a lot of repulsion so that they push away from one another. Okay? Timothy?
What if you did a triple bond?
We'll get into multiple bonds here in just a little bit. Okay? Because there's some things that we have to do before we can do a double or triple bond. All right? Any other questions right now? No? Okay. Okay, for this one, try to take it as far as you can. Total number? Put sulfur as the central atom.
Couldn't you add another one at the bottom?
Since we're only working with two oxygens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, so did we get to, at least get to this point? Okay, so no more electrons left. Is everybody happy? The oxygens, would you agree? The oxygens are happy, right?
Yes.
Sulfur, how many electrons do we show with sulfur right now? 6. So now, when we have run out of electrons, and that central atom still has not reached the octet, this is where we start making multiple bonds. And the way that we do that is we take a lone pair off of one of the outer atoms. Now, it doesn't matter which oxygen I take it off of in this situation. No, it doesn't matter which lone pair I take. No. So we're going to erase the lone pair off of the oxygen on the left, and we're going to make a double bond now between that oxygen and sulfur. So let's just kind of count to make sure that still everyone's happy now. So oxygen on the left, 1, 2, 3, 4, 5, 6, 7, 8. Okay, it's reached the octet. Great, grand, wonderful. We know the oxygen on the right is happy, right? So we don't have to worry about that. Now let's look at sulfur. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we only start making double or triple bonds when we have ran out of electrons and that central atom still needs to reach the octet. Okay? Questions? Any kind of questions? No questions? Okay. Try this one.
Is that what you did?
Hey, did you put 4 on here?
No, put one.
16 electrons?
Watch it does.
And this is how your skeleton structure kind of started off as? Did you make a double bond between the oxygen on the left and carbon? Then what's the next step you did? Nothing?
Made one on the other side.
Okay, so you took a lone pair off the oxygen on the right and made a double bond between that and the carbon? Anybody else set their little structure up this way? Okay, that is correct. Questions? Any kind of questions? Are we kind of seeing how this is working out some? Okay. Try this one. PCl5.
What do you mean? The five. I don't know where to put the fifth one. No, because yeah, the subtracting thing, because there's an extra chlorine. I don't know where to put it. Like a 4. What would you do with the extra one? Since there's 5 and
Can't put it on there.
Wait, so we can
Shoot.
do,
That's, put it on there.
but
It's like this
is
deal.
there, wait, no, I just have a question. Is there a rule saying you can only bind 4 atoms to like this? So you could bond 5 or no?
draw a line somewhere.
I like it.
Because so far we've only done this. See, we just, with this stuff, I go stair step out.
You just draw it somewhere. Yeah, I don't know. I'm gonna wait till he does it.
Are we coming up with a grand total of 40 electrons for our cache? And you put phosphorus as the central atom, then you start making single bonds to each of the chlorines. We got the 4, then, oh shoot, wait, we don't have just 4 chlorines, we have 5. So, like I said, 1 central atom, everything else is coming off the central atom. So let's kind of just continue on along with this humor me. How many electrons have we used up so far?
5 or 10?
10, so we have 30 remaining, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Now we're down to no more electrons remaining. Is everybody happy?
But there's
Actually,
yes, there's
sometimes the central atom can hold more than 8 electrons. Yeah. Sometimes, why? We can have what is called an expanded octet. Expanded octet means that the central atom holds more than 8 electrons to it. Okay? So phosphorus, one of those elements that can have an expanded octet. Alright? Now, one other thing I want you to put in your notes, put a star by this. Halogens as outer atoms will only have single bonds to them. Alright, so halogens are fluorine, fluorine, bromine, and iodine. When you see them as outer atoms, they only have single bonds to them.
Now, if they could have double bonds, would you make one of them a double bond?
If we needed a double bond, yes. Okay? Other questions right now? No? Okay, try this one. SF6. .48, right?
Yep.
Sulfur is your central atom. Yeah, I know. It's like, wait a minute here. Then you put 6 of the fluorines around sulfur. And each of the fluorine atoms put 3 lone pairs around them, and that used up all of your electrons. Are we done?
Yep.
Yeah. Okay, so another example of an expanded octet. Now, kind of an interesting side note. SF6. This compound, gaseous at room temperature, very heavy. Very, very heavy. Now, you went to the fair and everything, and got a helium balloon, float, tied to your wrist and everything, holds up. Did any of you try to poke a hole in that helium balloon and suck in the helium?